what does the acceleration of gravity depend on here on Earth? The radius. So the further you are from the center of the Earth, what happens to the acceleration of gravity? It becomes less. If you have less acceleration, then you've got less gravitational force and you weigh less. So I said move to the mountains, you'll weigh less. Much less? No. Because, I mean, the tallest mountain in the world is Mount Everest, which is about 5 miles tall. Compare that to the radius of the Earth, which is, what is it, 1,000 miles or something like that? That's not a big change. It's a very small amount of change. Now, if I take equation number 1 and 2, that's the letters, or the numbers in red, and I use them, I substitute them together. So what I've done is I've taken the acceleration, this equation up here. I've taken mass of the Earth, I solved equation number 2 for the mass of the Earth, just rearranged it, substituted it in, and simplified it. That's what you want. Right there. Now, if I'm at sea level, my distance from the center of the Earth is the same as the radius of the Earth, right? So what does that equation become? A equals G. Because I've got radius of the Earth, my radius, the same. That's 1. 1 squared is 1. Anything times 1 is itself. So A equals G at sea level, or at the average radius of the Earth. As I go higher, what happens to my acceleration? As I go higher into the atmosphere, my acceleration should become less. I experience a smaller acceleration of gravity. Smaller acceleration of gravity means less force. On the space shuttle, and the space station that they've got up there, what would be the neatest thing about being on the space shuttle? You'd be weightless, right? Because as Clinton says, there's no gravity. Is that true? Is there no gravity there? If there were no gravity there, could they be in orbit? No, because gravity keeps them in orbit. If there's no gravity, they're gone. They're going off in a straight line, and you're not going to get as many volunteers anymore. Yes. Actually, in the space shuttle, if we wanted to figure it out, and we won't go through it all, but the acceleration of gravity at the elevation of the space shuttle is actually 8.7 meters per second squared, compared to 9.8 meters per second squared on Earth. Now, why are they weightless then? Why do they feel weightless? They flipped that button. Now we're back to science fiction again, and we're going to talk about that. The anti-gravity boots. No. Well, not in our current knowledge of gravity. You'd have to somehow warp space and time in a different way. Ouch. Just hurt myself, I think. All right. Why are they weightless up there? Well, when they do astronaut training, they want people to experience weightlessness. One way they do that is in pools. All right? Because when you go in a pool, there's a buoyant force, right? You float. There's the buoyant force that keeps you up. That's because you're displacing water. That's an Archimedes thing. What's another place they do astronaut training, though? What about airplanes? They do it. There's a special name for the airplane that they actually use. called the vomit comet because what it is an empty 747. They've taken all the seats and everything out of it. And what they do is they take it way up into the air and then they let it free fall. Now, if you're falling at the rate of gravity, would you feel any weight? No. If you're in a plane and the plane and you are falling at the rate of gravity, you will feel weightless. All right? Now, they can only do that for a short period of time because after a while, if they do it too long, they run into the earth, and then you feel all the force at once. And again, it's hard to get volunteers to keep doing that. So what they do is they swoop it down, and I think it's like 10 seconds they can do it, and, go shh, and then you go back up and down, and that's why they call it the vomit comet, because you're doing this all the time, and people often will throw up. Which I don't know if you'd want to do that when you're weightless, because it just kind of floats there for a while. Now, so on the space shuttle, why do they feel weightless? There is gravity, so what must they be doing all the time? They must be falling. Think about it. If I take my ball, imagine you are inside the ball. Okay? It's a bigger ball. No, whatever. If I throw the ball horizontally, what does the ball start to do? Fall at the rate of gravity, right? So how would you feel inside the ball? You'd feel weightless. Let's go back to our original thought experiment we started the day with. We take the ball, we throw it very hard, and it follows the curvature of the Earth. What is it always doing? It's always falling. So how would you feel the whole time? Weightless. The space shuttle is following a curve around the Earth, and it is constantly falling. Well, what determines the radius of your orbit? That doesn't change. Speed. So if you slow down, what happens to your radius? It's going to get smaller, 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 smaller until you crash. And that happens to our satellites. Do our satellites we put up there stay forever? No. They fall out of orbit because there is some air resistance up there. Not a lot. So they're constantly slowing down. And satellites will fall out all the time. Speaking of, thinking of what we were talking about yesterday, I watched things too much. We talked about, as you go faster, time slows down. It also slows down when you're around massive objects, but we're not going to go into that. But as you go faster, time slows down, right? We talked about that, relativity. Now, satellites travel pretty fast. Space shuttle travels pretty fast. GPS satellites, for global positioning, have atomic clocks in them. Because you have to know exactly where those satellites are in order to triangulate your position using GPS. Because if you use a GPS, you're looking at different satellites, you have to know exactly where they are in order to figure out where you are. So you have to know exact things about time. They lose about, a third of a billionth of a second every day. All right, does that sound like much? If they don't correct for that, after the first day, your GPS will be off by 6 miles because of the distance and how far everything is apart. It's a lot of triangulation. So does 3/1 billionths of a second seem like a lot? No, but does 6 miles seem like a lot? If you got a GPS and you're trying to find your way out of the woods and you're, somewhere in 6 miles, and what else uses GPS besides us? Airplanes. Animals. You shop at a different Cabela's than I do, because all the other animals there are dead. Airplanes. Let's say you're landing an airplane by GPS. 6 miles or so good enough? Not really. Yeah, when you're landing, you want to be pretty much right on. Yeah. Well, I don't care what airport it is. I don't want to miss it by 6 miles. Because there ain't no runway there. Whether or not I take out a bunch of buildings, I'd feel bad for a second. You don't feel bad for long, I guess. All right. Enough on that. What you should do now, get your stuff done. Tomorrow I will have review questions for the test, and we'll see how that goes from there. Oh, we got to have that on there because it's fun.